You've probably seen those Russian nesting dolls, where each one opens to reveal a smaller doll tucked inside. Now picture an embedding, one of those vectors of numbers a model uses to represent meaning, built the very same way. The first slice of numbers already gives you a usable, if rough, sense of the meaning, and every extra number you keep just sharpens it a little more. That's the idea behind Matryoshka Representation Learning, from Kusupati and colleagues in 2022 out of Google and the University of Washington. Today we're breaking down how one embedding can be truncated to many sizes and still work. Let's start with the contrast, because it's the cleanest way to feel what's different here. A normal embedding is fixed size and all or nothing. If it was trained at 768 dimensions, you have to store and compare all 768. Chop off the tail and you throw away meaning at random, because the important information is smeared evenly across the whole vector. The Matryoshka version is nested instead. Training deliberately packs the coarse meaning into the earliest dimensions and the fine detail into the later ones. So you can truncate to 64 or 256 or the full length, and each shorter cut is still a perfectly valid embedding on its own. Where this really pays off is retrieval. So let's follow a single query through a two-stage search pipeline. It begins with an incoming query that we embed once. Because the vector is nested, that single embedding can be read at whatever length we choose, without ever rerunning the model. First, we search cheap. We use only the leading low-dimensional slice, maybe the first 64 numbers, to scan the entire collection fast and pull out a short list of promising candidates. This stage is where the memory and latency savings really come from. Then we search precise. We take just that small short list and re-rank it using the full-length embedding, spending the expensive comparison only on the handful of documents that actually made the cut. Out comes a final ranked list that's nearly as accurate as searching everything at full dimension, but at a small fraction of the cost. You paid for a cheap scan across the whole collection and an expensive scan across only a few survivors. Coarse to filter, fine to finish. Let's lock in the three ideas that make this so practical to actually deploy. The first is that it's nested, coarse-to-fine. Early dimensions carry the gist. Later dimensions add the detail. So every prefix of the vector is meaningful on its own. The second is one model, many sizes. You train a single embedding model, then truncate at serving time to whatever dimension your budget allows. No retraining, no separate models to maintain, and no awkward choice between a cheap model and an accurate one, because it's the same model at different lengths. And the third is shortlist, then re-rank. Fast course search followed by a precise pass over the survivors buys you big memory and latency savings. It's popular enough that OpenAI's text embedding 3 exposes it directly through a dimensions parameter. Let's pull together the 4 things worth carrying away from all of this. The Matryoshka method, from Kusupati and colleagues in 2022, trains one embedding whose first dimensions already form a usable coarse vector. Because detail is nested from coarse to fine, you can truncate to 64, 256, or the full length, and it still works. The deploy pattern is a fast coarse search to build a short list, then a full dimension re-rank of just those candidates, saving memory and latency. It's already mainstream, powering the dimensions parameter in OpenAI's text embedding 3. If you love seeing ideas like this nested open in plain language, come find us at standarity.com. We'd be glad to have you.